Hello everyone, a very good evening to all of you. I welcome you to the Net Zero Energy Building Knowledge Series. This is a series of webinars uh, that brings to you interesting and knowledgeable projects, ideas, tools and technology, everything to do with energy efficiency, renewables and net zero energy buildings. If you already tuned into our previous webinars, you know that we are in the third webinar in this month, and we have the entire next month and the months after it scheduled to bring you many different and interesting topics as well. Just a quick brief about it. This initiative is funded under USAID under the METRI program, which stands for Market Integration and Transformation for Energy Efficiency. So today we are going to have an interesting conversation with the panel of speakers on the project, which is the headquarters for MNRE, the Ministry of New and Renewable Energy. This is the first project in our series which is actually designed to be net zero. We do have other projects which talk about many different aspects of energy efficiency. However, this one is, from the beginning till the end, was intended to be a net zero energy building. So let's go further and understand what this building is all about and interact with our speakers. So just a little bit about me. I'm Deepa. I work at Environmental Design Solutions. I am an architect and a green building consultant. I lead all education-related initiatives at EDS, and I will be the session moderator today. Joining me, I have the expert panel of speakers who have actually worked on this building. First, I have Bedanta Saikia. He's the vertical head at Edifice Consultants. Bedanta has been an integral part of Edifice since 2000 and is now the vertical head. He believes that design should be unique, memorable, and monumental, but not at the cost of sustainability, environment, user comfort, and client satisfaction. Reading, researching, and attending seminars help him stay up to date in his field of work. A thorough gentleman, he works towards a perfect work-life balance. Besides endeavoring towards cutting-edge design and treating every project as his best, Bedanta enjoys traveling and spending time with his family. Some of the notable projects in his portfolio include the TCS Adibatla campus at Hyderabad, Infosys Indore campus, TCS Synergy Park Phase 1 in Hyderabad, Asian Heart Institute at Mumbai, among others. Joining him is Samdarsh Nayyar. You can probably see them right now. He is the founder of Green Horizon Consulting, a green building and sustainability consulting firm, and a director in Sunil Nayyar Consulting Engineers, one of India's leading MEP consulting firms. An engineer by education, he has a very strong background of designing resource-efficient building services and has been involved in MEP designing for a number of projects for Heinz, DLF, Commonwealth Games Delhi 2010, Lemon Tree Hotels, K. Raheja Corp, to name a few. He's a lead AP, Griha trainer and evaluator, IGBC AP, WELL AP, ECBC master trainer, BEE certified energy auditor and energy manager. He has been involved as a green building consultant for several projects. He continuously researches new cutting-edge technology and is proactive about applications in projects as well. So Bedanta was the head architect for this building, and Samdarsh was the MEP as well as the sustainability consultant for this project. Like always, I'd like to give a brief introduction before we actually jump into the project. This building is the headquarters for the Ministry of New and Renewable Energy in Delhi. It was actually a winning competition entry. So that is something interesting about this project. We'll hear from the team a little bit more about the competition and the process. The site area is about 2.76 acres, and this office building is 10 stories, about 240,000 square feet in area. Right now, the construction is ongoing for this project, and the building is also targeting a 5-star under Griha rating and platinum level under the LEED India NC rating. So quickly giving a little orientation about, taking a perspective as to why are we talking about this project. I think it's pretty obvious that since it's designed to be a net zero energy building, and this is the NZ knowledge series, it's very fitting to be in this webinar. So we want to understand what exactly was the process that went into designing a net zero energy building. How easy or challenging was it? So I want to now have a conversation with our panel members. Starting with you, Bedanta. Since this was a competition, could you please explain about the brief and the vision of the client? Because I think the brief from the client and the competition brief itself would have overlap, or probably it was the same. So just give us a little background on that.
Yeah, so the brief that we got, I mean, distinctly, it had to be a net energy positive building. That's what had come from the client. And I mean, apart from that, the brief was given to us that it had to be a iconic landmark building because Delhi is kind of it's in a prime area, it's at Lodi Road, and so it had to fit in the context of other iconic buildings as well. So
Right.
that's broadly the brief that was given to us, and we kind of worked on that.
Okay. So Samdarsh, when did you come on board in this project?
Yeah, so we were there in this project since the very competition stage, because as a part of the competition, we had to prove this building to be net zero energy, and therefore it was not purely a presentation of the architectural design and the aesthetics and the marquee nature of the building, but it was also a presentation of how, keeping all these aesthetics and the the landmark value of the building, how we would still be able to achieve a net zero energy status. How would we still be able to get the desired thermal comfort levels for the building occupants, which would actually be the ministers of the central government. And therefore we like, unlike other projects, for this particular building, we and Edifice, we together then collaborated right at the competition stage, and there we were.
Right. I think that gives a good orientation to the audience as to how this project got started, as a process. So going back to you, Bedanta, could you please briefly explain the project with the key features, and also in the process of, the actual design process, if the brief got modified?
Right. So apart from being a green building and kind of energy efficient building, what we tried doing in this building architecture is that we kind of tried engaging people as much as possible. So if we look at the site, it's a narrow site. So it's a narrow linear site. So the frontage of the building, which actually is from the secondary road, and from the primary road only there is a narrow strip of land that is connected to the primary road. So as a first step, we have taken the frontage as the that's for people. It's like where the people can interact. So that's where we kind of planned different spaces. We actually thought about a Urja Pavilion where people can come in till that particular point. It's kind of free entry, and beyond that point, your security starts. So that's where probably there can be different displays about energy efficiency, about the ministry. so that people start getting associated and getting familiar with this kind of a concept. And the challenges that we had was when you look at the site, as I said, it's a narrow site, and orientation of the site is predominantly east-west. So that we know that that's not right as far as if you want to design a building, a built mass which will take less amount of radiation from the sun. Ideal orientation is north south, the longer side being north and south. So that's the first challenge that we had. And obviously we cannot kind of go out of the site and design something. So we looked at options that are possible with us within the limitation of the site profile and orientation. The first few steps that we have taken is we kind of looked at the building as two wings, one being on the north and one being on the south. And we had the possibility of kind of tilting the south wing a little bit more towards the east, so that it's kind of protected from the western sun, and we kind of draw in natural light from the eastern side as much as possible. And the portion between both the wings, that north and south, that becomes your circulation core, that kind of becomes an atrium. And on the western side, so this, what you see in the screen is the lower floor actually, and we have all the public facilities on the lower floor, like auditorium or cafeteria. There's a crash and things like that. So all those public spaces on the lower floor. And as you go up, as I explained, the building is designed to be in two different wings, and the central pivot is where you have the main circulation core, and that is towards the west. And along the circulation core on the western side, we have other cores, that is mainly to have HVAC spaces, HUs or electrical rooms, or toilets, and the spaces that don't require any much of daylight, and which actually can become a buffer to the heat gain from the west. So those kind of spaces were kind of placed on the western side. And obviously, looking at the floor plate that needed to be designed, it was not possible that we draw in natural light only from one side. So what we have done is we have kind of broken down the cores on the western side into smaller masses, giving fenestration in between. So those are like deep punctures. And what it helped us to do is it kind of helped us to draw in natural light from the eastern and northeastern side, as well as from the western side, which is filtered. So as you know that, okay, kind of we had to produce electricity in terms of providing solar cells. So in the building mass itself, we have integrated the portion that can house the solar cells. So apart from that, we had also looked at various things like the building skin itself. So we proposed double wall so that the heat gain comes down. We looked at options like reducing the window wall ratio as much as possible, only give windows wherever is required to draw in natural light, so that the fabric gain of the building comes down. And since we also had to showcase renewable energy on the building, we kind of looked at why not integrate solar panels on the facade as well. So if you look at the south elevation of the design, you'll see that there are solar panels installed on the south side. So it kind of helps to shade the building on the southern side. At the same time, it becomes a part of the building facade. So it kind of helps to connect with the people, with the general public, and brings awareness about renewable energy being part of the facade. On the eastern side, where we have drawn the natural light predominantly, there we have proposed vertical fins. And on the fins, actually, we're proposing to grow creepers on the fins with some smart pots, so that the fins will help to cut down the glare from the east. At the same time, those creepers on the fins, that will also add to the environment that we know that Delhi doesn't have that kind of a good air quality.
Just one, I'm sorry to interrupt. We need to just take a pause for
Okay, so I was talking about the facade, as you can see on the present slide on the southern side, since we had to kind of showcase the renewable energy. I mean, that was one of the design intent. So we thought, why not have solar panels on the southern side, I mean, on the facade itself, so that people, the normal general public, can also get associated with the building. They are aware what renewable energy is. As you see, there are solar panels on the southern facade. And as I explained, predominantly the daylight, we're taking it from the eastern side, which we have tried tilting as much as possible to the northeast, the site being predominantly east-west oriented. And after doing that, we have proposed vertical fins because on the eastern side, what happens is in the morning, the sun angle is pretty low. The horizontal shading device alone will not help to cut down the sun glare and the heat. So that's why we introduce vertical fins on that side. And going one step forward, we thought that why not have some greenery on those facades, because that will help them to cut down the heat. At the same time, we're trying to send a message to the people about sustainability, about renewable energy. And Delhi, we all know that the air quality in Delhi is pretty bad. So, and we are taking up so much of space from the ground and building a building. So why not have greenery on the building facade itself? So that's the idea. We kind of proposed a green kind of a wall. It's not a green wall exactly. The fins are supposed to be having creepers on it with smart pots, so that that adds to the air quality of Delhi. At least it tries to improve the air quality around. And on the western side, as I mentioned earlier, on the western side, we have placed the cores of the building. That is your toilets, your staircases, your elevators, electrical rooms, UPS, places which don't require that much of a daylight, and that kind of adds as an insulation from the western side as well. And in between the cores, the punctures from where we are drawing diffuse daylight, on those punctures, we proposed green wall kind of a thing. So it's kind of on a trellis where you'll have creepers on planter boxes. So it shades the western side, the openings on the western side. At the same time, most of the common areas, including the lift lobby and other common areas, are proposed to be non-air conditioned. So these cutouts also help in cross ventilation to those spaces which are not non-air conditioned. So the idea was to kind of before we get into the numbers, we've been working very closely with Samdarsh in various projects, and the idea was to bring down the need of air conditioning as much as possible, because we all know that HVAC is something that kind of takes much of electricity. And to design a net zero building, obviously the first step is to reduce the need of electricity itself. So that was the first step. So we kind of took various measures to do that, starting from the orientation, tilting the building in the best possible way, looking at the building facade, reducing the window wall ratio, shading the building as much as possible. So those are the steps that were taken to reduce the need of electricity. And we kind of worked very closely with Samdarsh in terms of, since it was a competition entry, we didn't have much time. We had something like a month's time to come up with the architectural design, along with all the calculations to prove that it is going to be net zero building. So from day one onwards, we had to work very closely with Samdarsh. In fact, we had intermediate sessions to discuss and conclude on the wall sections. Presently, all the blank walls they have around, it's a double wall, 200 mm block work with a 200 mm insulation, then again an internal wall of 200 mm. So things like that, the height of the sail, height of the lintel to draw in natural light. So Samdarsh had done various analysis to check whether the natural daylight level is sufficient or not. So we went a little back and forth along with Samdarsh to kind of conclude on the design intent, architectural design intent. But what really helped us was that from day one, we try to cut down the fabric gain of the building, irrespective of whether this is going to be a net zero or not. That's normally the approach that we take for any project, whether it's a a net zero building or it's going to be green certified. That's a step we take for any buildings, anyways. I've not been able to. Okay, so on this slide, we spoke about the facade strategies of different size, different orientations. And what I was trying to explain is that as a standard practice for any project, what we do is we look at kind of reduce the need of electricity for that particular project. So that comes with the reduction of need of HVAC. That's the primary factor, because that's where most of your energy goes. And then secondly, obviously, the use of daylight, glare-free daylight that we look at using. So from day one onwards, we kind of worked very closely with Samdarsh on this project. And we, as architects, we tried to give him a building envelope that is as efficient as possible, so that he doesn't need to struggle much with his calculations. Because I have seen other projects done by others where what happens is we design a building envelope based on our aesthetical aspirations or things like that, and then we kind of get our MEP or sustainable consultants to break their heads to make into an energy efficient building. So that's not the right approach. So we always try to kind of design a building envelope which is energy efficient. Obviously, other things like aesthetics and building form and the space that you create, those things I could. Yeah, so as part of the design process, as I already kind of touched upon, we looked at the best possible orientation for the building. We looked at kind of reducing the fabric gain as much as possible, which includes strategies to have green walls, green areas, shading elements, introduction of themes, green screens, double walls with insulation. And we also looked at the possibility of drawing in fresh air and try creating some fresh air within the building itself. So what happens is, we all know in India, particularly in Delhi, the quality of fresh air is not so great. So, and when we had to introduce the solar roof, obviously the solar roof had to come with a big truss. So the space between the solar panels and the truss itself was that works out to be a pretty big, large void. So we thought that why not use that space kind of a greenhouse where we can have various indoor plants which kind of help to bring in fresh air, and you can draw that fresh air itself into the building. You can take that fresh air into the building system, which will actually help to reduce the HVAC load, and it will also give us better fresh air than trying to draw it from the external air. So those were certain strategies that we had looked at. And as I said earlier, integrating the solar roof into the building design, that was another challenge that we had. As you can see, the site is pretty small. It's only 2.76 acres, and the typical flow was hardly around, say, 25,000 square feet. And to have the solar power required, we needed around, say, 75,000 square feet of space to have solar panels installed. So the building roof was designed in a way so that it kind of can house solar panels as much as possible. We also looked at extending the solar panels to the solar pavilion. I spoke about the front narrow portion of the site, which was connected to the main road, where we wanted people to come in. Till that particular point, the security doesn't kick in. I mean, anybody can walk in. So that we looked at creating as a pavilion. Again, the roof of that pavilion, we looked at having solar panels there. So integrating that into the design was a challenge. Now, if you look at this present image that is there on the slide, you must be wondering that, okay, the images that I have shown earlier, there's a little difference. I mean, I'll try to explain the difference. Mainly, the roof has extended. If you have noticed, the roof has extended beyond the building line. So this has happened after we got the project. So what normally happens is that during the presentation or concept stage, client gives you certain information, like what will be the occupancy, and so we get certain information, we don't get certain information. And once we had all the information in place in terms of the actual equipments that they'll be using and things like that, then we realized that the solar panel area that we have designed during the concept stage, through which we actually backed the project, that was not sufficient. So we had to kind of increase the solar panel. So that's why if you look at it, the present building design, though the overall building mass and the design intent remains same, but that little modification of the solar roof that we had to do. Now, when we did that, another challenge that we have realized is the soffit of the solar roof. I mean, in the earlier design, what was happening was it was within the building line. Now, since it's getting extended, the soffit was getting visible, and the truss to support the solar roof, it was not that good a sight. So we had to introduce a jali pattern at the soffit of the solar roof. So that also has become an integral part of the design. Now we all know that when you design something in this part of Delhi, one approval that needs to be taken, that is from DUAC, that is Delhi Urban Arts Commission. They have to approve the design aesthetics, saying that okay, this fits in that particular area. It is contextual to the existing architecture of Delhi in that particular region. Then only you can kind of proceed. That approval is very much essential. So we looked at the building materials, maybe stone and jali patterns and things like that, which actually helped us to integrate the building aesthetics with other kind of public buildings in Delhi, and that actually helped us to get that particular approval. And as I move ahead, this indicates the site plan, the extent how the building has been placed. And as I mentioned earlier, the small dark gray patch that you see that is touching the main road, that's where the user pavilion is. So that is accessible from a station as well, from a metro station. So people can easily come there, and then that's kind of a public space that we wanted to create. So anybody can come and kind of hang out there. You can have different exhibitions there. So that kind of becomes a space where the ministry can exhibit their different, whether that's an event or they want to exhibit something. So it's kind of flexible space. It will only have a roof, so it kind of keeps interacting with the people. I'm trying to go to the next slide.
Yes, you are. Yes.
Okay, so I'm not showing all the floor plans. This is a typical floor plan. This is just to understand how we have placed the cores on the western side to block the harsh sunlight coming from the west. At the same time, between the cores, those punctures are where we kind of draw in natural light, diffuse natural light. And on the facade of it, in front of the windows, we plan to have a green screen. Basically, we'll have trellis and then creepers growing on it with a misting system so that it kind of reduces the heat. At the same time, we get a diffuse daylight into the floor plate. So the floor plate is around 16 meter wide. So we are planning to draw in natural light from the eastern side, eastern northeast, and as well as from the western side, which is screened through those niches. Yeah, so I spoke about the importance of the fabric design. Samdarsh will be able to add to the numbers better than me. But if you look at it, the wall sections, we actually went there with a 400 mm thick wall section. I mean, this comes as a knowledge. When I was talking to Samdarsh at the beginning of the project, one important thing that he told us that in Delhi, all the public buildings that you look at, I mean, the old public building, they have very thick walls, so that it doesn't allow the heat to get inside, and that works as the first barrier of heat getting inside the building. That's why we thought of, why not kind of have a similar kind of system in our building as well. So we went into the 200 mm thick wall with a 200 mm insulation and again a 200 mm wall inside. So that helped us to achieve a U value of 0.1. for the wall. And the roof again, it was a 150 mm RCC slab with insulation of 150 mm. So we tried to insulate the building as much as possible from the harsh summer of Delhi, from the heat of Delhi. So with the roof insulation and things like that, again, U value was brought down to 0.4, as you can see in the chart. And glazing, we went with high performance external glazing with low A glass. It's 6 mm glass, 12 mm air gap, and 6 mm glass. So this again helped us to bring down the U value to 1.8. And we kind of looked at reducing the amount of glass as much as possible, reducing the amount of windows as much as possible. So the window wall ratio, if I'm not wrong, it was around 26 to 27% what we achieved in this particular building.
Right.
Right. So in the next slide, it explains it. I was just trying to explain. This is actually the minister's cabin, and pretty lavish. It's a simple design, and minister's particular floor is recessed a bit. So what you see from inside out, that greenery outside, that is actually we are proposing to have it in the balcony that the minister's floor has got. So what they get to see outside is that greenery, because in all our design we believe that the architecture should not become a barrier between inside and outside. It should help to bring in the outside in. So biophilia is something that we know that it helps all of us. It kind of helps to bring down the stress level. So in interiors as well, we try to introduce as much green as possible, and continuing that, we are kind of planning to have indoor plants in this particular project, which will give you better quality of air inside, and it will kind of help us to get oxygen rich air inside the building. And talking about daylight, around the flow plate, the usable flow plate has got good amount of daylight, so not dependent on artificial lighting that much. And so it gives you a good amount of daylight. At the same time, it kind of keeps the connect with the greenery outside.
Right. Yeah, I think that's a good overview of the building architecture. You know, you talked about orientation and walls, basically the building envelope and the planning and the massing. This is, I mean, at least I can understand that this has really tried to bring down the loads, the thermal loads and the associated energy demand must, quite significantly. So now I want to hear from you, Samdarsh, about the building systems, the space conditioning systems. Could you briefly explain with the key design features in this?
Sure. Before I start on that, so as you know that we are striving for the net zero energy status, and the step one for that, which we have already discussed, to minimize the heat, like entering the building, from the envelope. And then the step two, which I would say here is, the optimized building systems, building energy systems. So what we now talk about is basically point two, which is selection of an efficient building system. Now, when we talk about the air conditioning load, which is almost about 50 to 60% of my building energy consumption, followed by lighting, which is about 10 to 15%. It used to be like higher earlier, but now with the LEDs and energy efficient lighting, it contributes about 15%. And then of course we have a fixed load, which is the receptacle load, which is the power points, the workstations, the computers, printers, UPS, servers, which is kind of fixed, whether it's a green building or a non-green building. We can use energy efficient, systems, but it's kind of a fixed load. And then we talk about miscellaneous load. So if I talk about building air conditioning, the entire system is a water cooled central plant. We have got water cooled chillers which are placed in the basement, and these chillers are working with cooling towers which are provided with variable speed drives. These cooling towers are not on the building terrace but at the site level, which has helped me to reduce my pumping from the chiller to the cooling tower. So I need not pump it all the way up to the terrace, but I just need to pump it to the site level. Now so this is primarily the high side part, and also when we talk about pumping and chilled water pumping, there are different systems. So if you can just go back to the slide before, please. Yeah, so when we talk about pumping, and we are aware that there are chilled water pumps and there are condenser pumps for the cooling towers. So in a typical conventional building, you will find primary pumps and you will find secondary pumps. Primary pump is for pumping, across the chiller, and secondary is for pumping into the building. But here we removed the secondary pumps. We used primary pumps for both the chiller, cross section as well as the building load, something called as a primary variable, which we have, now been using in number of buildings. So this helped me reduce the number of pumps. This also helped me reduce the kilowatt installed of the plant. And then when we talk about the internal distribution, so if you can now move to the next slide, please. I have clicked that, yeah. Okay, so now we have, now when we talk about the internal low side, air distribution strategy and cooling strategy, we proposed a mix of radiant and conventional. I think there is a miss in the slide. So we have two chillers. One is a 215 ton. So please don't read as 15. Please read it as 215 ton radiant chiller. And we have a 215 ton conventional chiller. So when we talk about any typical room, say for example, the minister room, which Bedanta was showing. Now that room has got ducting coming from the air handling unit, the floor mounted AHU, which will supply cold air into the space. Plus there are radiant ceiling panels, radiant baffles, which are also there, in the minister room. So what happens is that when we talk about a radiant system, and when we talk about any building's air conditioning, there are primarily two types of loads. One is sensible load and other is latent load. Sensible load is the load primarily on account of difference in temperature, delta T. And latent load is the load on account of humidity, which is your conversion of water to water vapor. So the temperature remains the same, but there is a change in the phase. So when we talk about places like Mumbai, places like Chennai, there the loads are high because of latent. But when we talk about Delhi, here loads are high because of sensible. Now when we design radiant, radiant can only take care of sensible load. The humidity load and the fresh air, those have to be always provided through the air handling unit. So therefore, what you see here is basically a hybrid system. And in a hybrid system, we have a conventional chiller, we have a radiant chiller. The conventional chiller takes care of the latent load and the fresh air load, and the radiant chiller takes care of almost about 70 to 80% of the sensible load through baffle. Now, then in terms of the selection of equipment, if you can see here on the slide, we have CTI certified cooling towers. Cooling towers fans are also with variable frequency drives. We are using heat recovery based fresh air system. So what does heat recovery based fresh air system does is that when we talk about raw fresh air, which is at fresh air at 43 degrees Celsius, I have to cool it down to 24 degrees Celsius to supply inside a room. But what heat recovery wheel does is it takes the exhaust from the toilet. So when I am supplying a space with fresh air, that space is getting over pressurized, which means I have to also remove some air from that space, or maybe from a toilet exhaust. Now that toilet exhaust air, which is cooler in temperature, say around 27-28 degrees Celsius, we make that air to exchange heat with the raw hot fresh air. So it's kind of pre-cooling of that raw fresh air, so that 43 degrees Celsius fresh air pre-cools to 35 degrees by heat exchange with the exhaust, and then that reduced load is on the chiller or the cooling coil. So we have used that heat recovery based system. That also heat recovery is with a dual coil. Dual coil means one is the cooling coil coming from a radiant chiller, and the other cooling coil is coming from the conventional chiller. And we should also be mindful of the fact that a conventional chiller works at 7 degrees Celsius, 12 degrees Celsius, which means that it supplies water, chilled water, to the air handling unit at 7 degrees Celsius and takes that hot water back at 12 degrees Celsius, whereas a radiant chiller works at 15 degrees to 19 degrees. It supplies at 15 degrees and takes back at 19. So by very virtue of this delta T and the higher temperature range, radiant chillers are typically working around 0.45 kilowatt per ton, and a conventional chiller is about 0.67 kilowatt per ton. So almost about 33% saving just by virtue of operating at a higher set point. And then when we talk about hot water generation, which is also required during a couple of months during winters, and being a minister's building, and the ministers and the IAS officers, they have this habit of even working late in the night, and therefore they would require winter heating. Conventionally, people have been using electric boilers, which are also called as hot water generators, which are extremely inefficient but cheaper. And what we have proposed is basically a reverse cycle heat pump. So the way we have an outdoor unit of a VRV or a split unit, so what does an outdoor unit do? Outdoor unit throws in hot air. Now what if I use that hot air to generate hot water? So this is what something called as a heat pump. So it basically works in a reverse cycle. It generates me, gives me hot water. It is about 4 to 5 times more expensive than a hot water generator, but almost about 1/6, 1/7, a power consumption. So the next slide, if I move, also to add, when we talk about variable frequency drives, now when we talk about indoor air handling units, they have got VFDs, we are all aware of that. So on the fans we put VFDs, variable frequency drives, even on the pumps we put VFDs. In this building, in the air handling units, and also you can see on the slide basement ventilation fans, we have used something called as a EC motor. So what an EC motor is? It is like that fan regulator which we used to have earlier in the houses, which we can rotate from 0 to 100. So it takes a complete turn from 0 to 360 degrees Celsius, and this is how the fans work. So you completely remove the need of a variable frequency drive. We should also know that VFD are also resulting into harmonics, which is also a big issue in the buildings these days, and you have to put harmonic filters. So we remove VFD, we remove harmonic filters. These EC fans are DC motors, 0 to 10 volts, and they can give me the same variable performance which a normal DIDW fan with a VFD gives. And then when I talk about this particular slide, so we already discussed about the heat recovery wheel. One very interesting thing, and I'm sure the audience here must have also done a lot of similar projects, like offices. Now when we do thermostats and we have a VFD with AHU. So for example, if there are 10 cabins and every cabin wants to maintain a different temperature, some wants to keep 23, some wants to do 24 degrees Celsius. So there is something called as a VAV box, like a variable air volume box linked with a thermostat which is there in the cabin. Now what happens is, if you come to Delhi during any winter month, like for example in my own office, I would simply turn the air conditioning off because I'm feeling cold with the draft of air. But what about the oxygen? Whether it is winter, whether it is summer, don't I require that minimum critical airflow into my room? So in this particular building, we simply did not link the air conditioning system with a thermostat. We linked it with a CO2 sensor as well, and we made sure that every room will also get that minimum bleed, because when the ministers are sitting there, one of the conditions, though not a part of the RFP document, was that the air quality in Delhi is very, very poor, especially during those winter or the transition months. So we also made sure that this building also takes care of that. And when we read the ASHRAE standard, they say 5 CFM per square feet plus 5 CFM per person plus 0.06 CFM per square feet as the fresh air requirement. And there is a note which states that if your air quality is very good, you can remove that 0.06 CFM per square feet. That means with a better air quality, you can reduce your fresh air requirement, you can reduce your fresh air conditioning loads. So we are trying to do all these systems into that. Then when you come further down, we have taken all pumps to be IE4 rated. Even if you go out today in the market, you would find that IE4 rated is not easily available and they have a long lead item. But then 3 years back, we convinced the client that, sir, even though it is 3 years, there is a long lead, in this, but these products are available, and let's go for the most efficient pumping system available, in the market. So my pumps, my motors for air handling units, ventilation fans, heat recovery, everything is IE4 rated. And one very important thing, plant optimizer. Now, what happens is that we all know buildings have got BMS, but BMS have simply been reduced to being a plant, operator. Turn the chiller on, turn the chiller off, turn the pump on, pump off, scheduling, cycling. But what plant optimizer does is puts a cap on the energy consumption. So for example, if I feed into the software, please limit my power consumption of the central plant to 0.7 kilowatt per ton, including chillers, pumps, cooling towers, it would make sure that everything is working in a combination. So for example, whether to run one chiller at full load or two chillers at 50% load, it will see the graph, the curves of all the equipment, which we also feed into the simulation softwares, and make sure that the optimal combination of plant is working. Next slide, please. Right. Then when we talk about lighting, which is the second, major energy consumer, we all know that we talk about, office lighting. We started with 1 watt per square feet, 7-8 years back. It came down to 0.8, 0.7. Now, I believe the average is 0.5 to 0.6. What we are using here is 0.35, rather 0.32, is what we have achieved now, watt per square feet, getting, getting an average lux of about 340 and a uniformity of 70%. We have, so there is a term which we use, I'm sure you must have all also read in the ECBC. It's called luminous efficacy, which is lumens per watt. That is the output of a light fixture in lumens divided by the power consumption input power, which is wattage. And the fixtures which we are using here are 165 lumens per watt, whereas what the regular brands giving in India like Philips and Wipro and Bajaj, maybe 120, 130, maybe going up to 140. But this is the product which we are using, 165 plus lumens per watt, and we have been able to get this. Similarly, for car parking areas, it is 0.1 watt per square feet. And plus, like as I mentioned, that all the fixed loads like the receptacle, power points, workstations, we have told the client to buy, Energy Star rated, and then the entire office is with occupancy and daylight sensing with dimmable blasts, DALI based. And next slide, please. Yeah. Okay, so then what we did is we did our Deepa, this is not that, can you please check if there is a slide before this? I'm not sure.
Yeah, Samdarsh, this is what we have.
Okay, fine. So now what we did is then, so once we close the two stages, which is the optimal building design, and then we come to the, the optimization in the building energy systems, then we arrived at our, net zero equation. So we found that our daily power consumption, the peak power consumption of the building is 5126 units. And so then we discussed with, Vedanta and the Edifice team in terms of maximizing the solar area, and the total area available for solar, after creating that secondary roof is 7413 square meter. And we usually, one kilowatt of solar if we go for a 15% efficiency panel, which are usually available in India. They take about 10 square meters of space. But for this particular building, we proposed the client to go with sun power, which is also installed at the Indira Paryavaran Bhavan. So that has got an efficiency of about 24%, and 1 kilowatt takes about 7 square meter space. So with this, we were able to accommodate 1059 kilowatt peak of solar on the rooftop. And the annual average is roughly about 1500 units, but the daily average is about 4.5 to 5 units. So we were able to generate 5 to 95 units per day. Now this is what we presented to them during the competition stage. But if I give you the statistic of today, because it's been 3 years and design has also evolved, so the annual energy consumption of the building comes to around 12,26,000 units, 12.26 lakh units. And the annual energy generation, we have done 3 options, one with sun power and other with Panasonic. With sun power panels, we are generating almost about 17.5 lakh units, which is 5 lakh more than the required. And with a Panasonic panel, we are getting about 15 lakh units. Panasonic has a 20% efficiency, and sun power has a 24%. So 12.25 lakh units, is what the building requires annually. 15 lakh is what we are able to generate with a 20% Panasonic, and 17.5 lakh units is what we are able to generate with a 24% sun power panel. This is the current stat, and this is how now the building is getting executed at site. Next slide.
So that pretty much. Hello, Samdarsh, would you like to add anything else to the points that you've mentioned?
Yeah. So this is primarily how we have been able to achieve net zero here. And in terms of, if I give you some stats, typically when we talk about building, we talk about 10 to 11 watt per square feet as the connected electrical load. Green buildings can go maybe up to 7 to 8 watts per square feet. 7 to 8 will include everything from air conditioning, lighting, everything. This building, we have been able to achieve 2.4 watt per square feet as our demand load. And this is how I would say that we have been. So the biggest challenge I would say while designing this was that this was not a large site where there is an like an ample space to put up a solar farm. The biggest challenge for this design competition was that it was a 3.5-acre site, and it was a fully built with 3 basements and ground plus 7 floors and fully air conditioned building, what the client aspired for. And we had to do a reverse engineering to see what is the maximum solar potential possible at the site, because when we talk about New Delhi, we do not have any other renewable energy other than solar. There is no wind available. And then we had to reverse engineer and come back to Vedanta that, sir, now we need to reduce the building load, the building energy consumption to this by putting this as the wall thickness, because when we increase the wall thickness, we also lose on the FSI, because the thickness of the wall is also counted. So there is a trade-off, and therefore that reverse engineering, when we presented to the competition panel, basically helped us to convince them that this is how we will be achieving net zero. Yeah. So that's it from me, Deepa. Thank you.
Yeah. Thank you so much. That was very comprehensive, explanation of all the different mechanical, space conditioning, and other MEP systems in the building. I mean, quite clearly, it took the design to the next level by using this extremely efficient technology, which is pretty evident from what you've explained. In fact, you've also covered some of the constraints and other challenges we wanted to talk about, which is already good. And of course, we are running a bit short of time. So I want to now go to my question about the NZE experience. So I want to ask you, Vedanta, Samdarsh shared some of the constraints that went in, from his perspective. I am curious to know if, you know, you also spoke about design constraints, but in your vast portfolio, this is the first net zero energy project, right? In your work experience so far. So, from your perspective, how different was the design process from other projects? Is it more time intensive, or you think it calls for a more, or maybe a different expertise, other
See,
than, of course, the constraints you spoke about?
See, as architects, I believe, in fact, we believe as a company that it's a duty and responsibility to have designs which are energy efficient. So each and every project that we design with that particular approach. So whether it is a net zero building, whether it's going to have any green certification or not, we ensure that all the design that we do is energy efficient. That's one of the primary thing that we look into each and every design, apart from all the other things like aesthetics, creating quality of spaces and things like that. So though it was our first net zero building, I would say the architectural part of it, in terms of giving a very efficient building envelope, that hasn't changed. Whether if I compare with another building that probably have designed, which is not a net zero. Only thing that is different is definitely, since it is a net zero building, we had to integrate the solar panel in the building. So that had to be looked into as a, so you cannot just add on that particular thing into any building, or so it has to be integrated part of the design. So that is something, it was different because we had to integrate the solar panel into the building design itself. So it all looks designed. It doesn't look like an add-on kind of a thing. So that was different. Apart from that, bringing down the energy load by giving a good building envelope, orientation, massing, those kind of things, those are, I'd say there's no difference as such.
Okay, so that's good to know that overall the thinking process is not really different. But of course, when it comes to renewable, there has to be a thought into how it will actually get integrated into the building.
Yes.
And of course, I wanted to ask about constraints, which you've already covered as well. So now, quickly, we have the next 5 minutes for this last question from me. And after that, we will take the questions from the audience. So actually, I want to ask you, Vedanta, from an architect's point of view. I know this building is still under construction, but having gone through this process, do you think there are any key elements that you can point out to designing a successful net zero energy building?
Yeah, I think the first point I've already explained that, as architects, it's our primary responsibility that any building that you design, any structure that you design, has to be energy efficient as much as possible. And the key thing to that is that we should design the building where the need of air conditioning is reduced as much as possible. That is the first step. And the second step, I would say, which is equally important, to work closely with the MEP and sustainable consultants to achieve a net zero or energy efficient building. Because as architects, we have the basic idea about how to make the building envelope energy efficient by taking care of the building facade, orientation, and things like that. But to take key decisions like actually what is the window ratio that I need to give, whether it's 27% is working or there's 24% is working. What is the window section that I need to look at to have sufficient daylight inside? That too is glare free. What is the wall section that I need to look at? So things like that, which has to be kind of coordinated closely with the MEP and sustainable consultant. For instance, in this design, from day one, we knew that we'll be going with radiant cooling, and that's something that we kind of have discussed with Samdarsh. We looked at all the options. What are the options of radiant cooling that we can look at? Because all that is integrating those things into the design, it has got different things. I mean, starting from space that you need to give. For instance, in radiant cooling, obviously it takes less space because there is no big HU rooms. So your utilization of space is better. But what I'm trying to highlight is that certain decisions that needs to be integrated into the design, which is not possible if we don't work closely with MEP and sustainable consultant from day one.
Right. And again, similar question to you, Samdarsh, from you're already researching cutting edge technologies, whether it is to do with solar or MEP. Uh, how would you like to summarize for our audience about the key elements that go into creating a successful net zero energy building?
Um, You see, I think to start with, I mean, Vedanta has already said that when we see net zero and the building envelope, but I feel that we first need to really understand what the client intent is, the client mandate is, and then net zero. If I talk about in a straightforward layman's term, it is the energy. It's never the connected load. This is where also people tend to mix up. It is the energy consumed and the energy produced, and the key focus area has to be the part one, which is the energy requirement of a building. What best I can do to reduce that energy, but at the same time we have to be mindful of the fact that not at the compromise of human health and comfort. So there have been instances where we aspire to be net zero, but we achieve up to 60-70%. We do not achieve 100% because maybe that particular solar is not available. But even that 60-70% is also a big achievement, because I am able to give that desired thermal comfort. I am able to give that desired lighting levels, lighting comfort, that desired acoustic comfort. So we need to also be mindful of the fact that while we do net zero, but occupant health and comfort, that buildings are designed for occupants and not vice versa. Somehow in our pursuit of net zero, we should not forget that. So I have also seen instances where that compromise is also happening. And I mean, as Vedanta said, prime focus is to reduce the energy. And then once that has happened, then believe me, these days when I am doing research on alternate technologies, solar may be one of them for projects in South India or in Maharashtra. We also have wind. We also have horizontal windmills. I am also exploring something called as a hydrogen fuel cell. We even have things like biomass. So there can be several opportunities, which can be made available to generate that power. But the first step is, let us have that right mix to have the optimal thermal comfort and the minimalist building energy requirement.
Right. Well said. I think that is the crux of any good building design, even whether the goal is net zero or not, is to reduce the energy demand. That's like the first step. Of course,
Right.
if it comes from the client in the vision and the brief, then it's a lot more effective. But that said, there is always opportunities for buildings to actually look into those areas where they could reduce the energy demand. And
Right.
renewables then is in the last step in this process.
Sure.
So with that, now it's time for taking questions from our audience. So I'm going to take one question at a time. So the first question is from Trupti. What is the material for the vertical fins on the east side? East facade, I think she means. And what are the creepers tied around?
Yeah, this Vedanta here. So Finside has got a MS framework which has got a net tied to it, and we are exploring creepers like money plant to be grown on smart pots there. So that we are hoping that it will kind of grow on the fin, and which will shade us.
Okay. The next question is, how did you integrate the jali into the soffit of the roof? What is the material used? Is it a false ceiling or structural?
Unfortunately, it's a false ceiling. So we are looking at probably doing it at GFRC or metal as an option. So we're looking at those two things. It's sort of soffit. It's a false ceiling. It's not part of the structure. It's actually hiding the structure which is above.
Okay. Next question is, from Akshay. Is the structure to support the solar panels on the roof part of the FAR?
No, it is not part of the FAR.
Okay. Then the next question is from Ashok. What impact does introducing biophilia has on water demand?
See, I mean, first thing that we need to look at is that biophilia is something that's very important. I mean, we are as human beings. I mean, if we look at our evolution as humankind, as a species, most of the time we've spent in jungles, in caves. Okay, so we have a direct connect with nature. And so that is something we need to seriously look at. And we believe that that is something we should not be compromising at all. And believe me, the water demand is not much. We can look at drip irrigation. That's why I was talking about smart pots. So it kind of, it only consumes very little water as possible. That too is in forms of drip irrigation. And by doing water conservation and doing recycling of water, that water demand is made by the building itself.
Right. Then the next question is from Sunny. What has been your strategy for selection of the materials?
See, normally for a green building, we look at materials that has got a less carbon footprint, less embodied energy in it. And at the same time, we use materials that has got low VOC and things like that. A paint that has got low VOC, material that has got less embodied energy into it. So that's the primary thing. And then, I mean, obviously, as a key thing which comes into it is that you select materials within the vicinity in terms of any finishing materials or any material that you use in a building that's within the vicinity of that particular area.
And we have we have time for one last question here. What is the cost difference, even if it's estimated, from a conventional office building, and what is the payback period for that?
I think that should go to Samdarsh. As far as the architecture is concerned, I'd say no. I mean, because as I said, as responsible architects, this is our responsibility to make any architecture as energy efficient as possible. So that is a given. I mean, if you're thinking that, okay, I'll only design the building as an energy efficient building if the client is asking me to go for a net zero or for a certification, which is wrong, which we believe. So with that idea, the cost for the structure as far as energy efficiency, I mean, for net zero is concerned, the architectural part of it there's no difference as such. Yes, if you're going for net zero, then you have to produce that energy. So that will call for additional solar panels and things like that, which probably any other building will not have. That's additional cost. For the systems that are getting installed, yes, probably Samdarsh can highlight on that. That may have some additional cost to it.
Yeah, to just I mean like add to Vedanta, I recall that when this building was also estimated, and we were also asked by the client to give a differential, and for a conventional building, the cost was coming approximately around 4,800 rupees a square feet, which includes everything, which is your civil work, structure, MEP, interior, finishes, false ceiling, flooring, etc., etc. And then the client asked us to give the estimate for this building, which is a net zero energy building. That came to roughly about 5,600 rupees. That also including 1 megawatt of solar. So if I remove the solar, we come down to somewhere around 5,100 or 5,200 versus 4,800. So that's roughly about 7 to 8% increment compared to a conventional building. And being a government job, we had to always give the costing with the supporting offers and all. So this was the metric then.
And here's the last sort of a appreciation comment from Trupti. Samdarsh and Vedanta, great job. Many congratulations. How can we contact you for your services?
Thank you. We can share, our email ID across, and we'll always be there to help you out.
Yeah.
Yeah, same here.
So we can also share that with the participants. So.
Yes.
So I think we don't have time to take more questions. Actually, they are coming in, but we are slightly overshooting the time given that there were some issues in the middle, but we did extend the time accordingly. So with that, we have now come to the end of the webinar. I thank my panel, Samdarsh and Bedanta. Thank you so much for taking out time from your busy schedule and sharing this wonderful project in such a great detail with the audience. Thank you so much to all the attendees in the webinar. I really apologize for the technical glitch which happened in the middle. We'll make sure that doesn't happen again for the upcoming series. So thank you everyone, and see you in the next webinar.
Thank you, Deepa, and thank you everybody. Thank you, Bedanta. Thank you.
Thank you.